we learn about moment generating function MGF of a random variable and its properties. Let us see the definition. The moment generating function of a random variable capital X about the origin. The moment generating function of a random variable capital X about the origin is denoted by the symbol mx of t, is denoted by the symbol mx of t, and it is defined in the following two ways. The basic definition is mx of t is equals to expectation of e power tx. Mx of t is equals to expectation of e power tx. Expectation of e power tx. Here, this e represents the exponential function. Here, e power tx represents the exponential function. Suppose here the random variable is discrete, then we use this definition: summation x e power tx p of x. Suppose the random variable is continuous, then we use this definition: integral e power tx f of x dx. So observe that. One of the very important definition of the random variable, moment generating function of a random variable, which is simply denoted by MGF. MGF, moment generating function of a random variable. The moment generating function of a random variable capital X about the origin is denoted by mx of t, is denoted by mx of t. You must write capital X in the suffix mx of t and defined as expectation of e power tx. Expectation of e power tx. Here, that random variable capital X may be discrete or discrete or continuous. Here, the random variable capital X may be either discrete or continuous. If the random variable capital X is a discrete, then mx of t is equals to summation over x e power 2x p of x for discrete random variable. Suppose if capital X is continuous random variable, then the same mx of t is equals to integral e power tx f of x dx. Remember that in case of discrete random variable, we use summation and p of x, probability of the particular events. Summation p of x means this represents the with corresponding probabilities for the values x1, x2, and so on xn. And if the random variable is continuous, we use integral symbol. We use integral symbol e power tx f of x dx, where f of x represents probability density function. That's it. That's it. Now let us understand this definition in depthly. Mx of t is equals to expectation of e power tx. Expectation of e power tx. We know that the exponential function is defined like this: e power x is equals to 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus and so on plus x power n by n factorial plus and so on up to infinity. E power x contains infinite number of terms. The series of e power x contains infinite number of terms. Instead of x, we have tx here. Instead of x, we have tx is there. So expectation of 1 plus tx by 1 factorial plus t square x square by 2 factorial plus t cube x cube by 3 factorial plus and so on, t power x power r by r factorial. Remember that, plus and so on. This is wrong here. You cannot conclude like this. Here, it contains infinite number of terms. So, plus and so on. Plus and so on. There are infinite number of terms. Remember that. So, after that, let us split the expectation. So, expectation works on x only. Expectation works on x only. So, here t is the parameter. So, it can be written like this. Expectation of 1. Expectation of tx, t into expectation of x, plus t square by 2 factorial into expectation of x square, plus t cube by 3 factorial into expectation of x cube, plus and so on, t power r by r factorial into expectation of x power r, plus and so on, infinite number of terms are there. So here you remember that expectation of t power r by r factorial into x power r is nothing but t power r by r factorial into expectation of x power r into expectation of x power r. And we know that expectation of x is equals to mu1 dash, expectation of x square is equals to mu2 dash, expectation of x cube is equals to mu3 dash, and so on. Expectation of x power r is equals to mu r dash plus and so on. This is nothing but summation r is equals to 0 to infinity. Summation r is equals to 0 to infinity t power r mu r dash by r factorial. This series of terms can be represented like this. Summation r is equals to 0 to infinity. Summation means sum of the terms. Summation r is equals to 0 to infinity t power r mu r dash by r factorial, where mu r dash is the rth moment of capital X about origin, where mu r dash means it is the rth moment. It is the rth moment about the origin, and it is given by the following formula. Mu r dash is equals to this one. Mu r dash is equals to integral minus infinity t plus infinity x power r f of x dx for continuous random variable, summation x power r p of x for discrete random variable. That's it. What is mu r dash? Mu r dash is nothing but the rth moment about origin, and it is given by the formula mu r dash is equals to integral minus infinity to plus infinity x power r f of x dx for continuous random variable. For discrete random variable, it is summation x power r p of x. Observe that. Here mu r dash is the coefficient. Please observe that. Mu r dash is the coefficient of t power r by r factorial. Coefficient of t power r by r factorial in the expansion of mx of t. Since you observe here, since mx of t generates the moments, so it is known as moment generating function. This is the definition and the story behind the definition of this moment generating function. Let us see the properties of moment generating function. The properties of moment generating function. The first property, mcx of t is equals to mx of ct, where c is a constant. Like this, mcx of t is equals to mx of ct, where c is a constant, and mx plus y of t. Observe this, mx plus y of t is equals to mx of t product mx of t into my of t, and max plus b of t is equals to excuse me, max plus b of t is equals to e power bt mx of at, and mx minus a of t is equals to e power minus at by c mx of t by c. Fourth property is known as effect of change of origin and scale of mgf. The fourth property is known as effect of change of origin and scale. And the last one, this is the extension property. This is nothing but extension property of second property. Here we use only two random variables, x and y. Here we use n random variables. mx1 plus x2 plus and so on xn of t is equals to mx1 of t into, here it is product, mx2 of t into, again it is product, and so on into mxn of t, which is also known as the additive property of moment generating function. Property number 2 and property number 5 are known as additive property of moment generating function. Observe that. This is the one of the very important question. Define moment generating function and write its properties. Sometimes exclusively they ask about the proof of these properties. Sometimes, but it is rare case. sometimes they ask about the proof of the properties of moment generating function. So let us learn these proofs also. The first property. What is the first property of moment generating function? For any random variable capital X, and any constant C, mcx of t is equals to mx of ct. For any random variable capital X and any constant C, mcx of t is equals to mx of ct. Observe that. By the definition of moment generating function, we have mx of t is equals to expectation of e power tx. This is the definition of MGF. By using the definition of moment generating function, mx of t can be written as expectation of e power tx. Now replace capital X by cx. Let us write cx in place of capital X. We get this step. mcx of t is equals to expectation of e power tcx. That's it. Let us go for the next step. Expectation of e power ct into x. Observe this condition. mx of t is equals to expectation of e power tx. mx of t is equals to expectation of e power tx. So this expectation of e power ctx can be written as mx of ct. That is the required one. So this is nothing but mx of ct. Therefore, mcx of t is equals to mx of ct. Let us see the second property. Property number 2. Let capital X and Y be any two random variables. Then mx plus y of t is equals to mx of t my of t. mx of t into my of t. This is known as additive property of moment generating function for two random variables. This is known as additive property of moment generating function for two random variables. Right? Again, this is also simple proof. By the definition of mx of t, by the definition of MGF, mx of t is equals to expectation of e power tx. Now mx plus y of t. Here just we replace the variable x by using the variable x plus y. We are replacing the variable x by using the sum of two variables x plus y. That's it. mx plus y of t is equals to expectation of e power t into x plus y. Expectation of e power t into x plus y. Again, this is nothing but t into x plus y. T into x plus y can be written as tx plus ty. That's it. Expectation of e power tx plus ty. We know that this is the general property. We know that e power a plus b is equals to e power a into e power b. By using that property, this e power tx plus ty can be written as e power tx into e power ty. So this is in the form of expectation of xy. This is in the form of expectation of xy. What is the property of expectation of xy? We know that it is expectation of x into expectation of y. In the previous lecture, we learned about this. Expectation of xy is equals to expectation of x into expectation of y. By using that property, this term expectation of e power tx into e power ty can be written as expectation of e power tx, expectation of e power ty. Apply the definition of moment generating function. Expectation of e power tx, mx of t. Expectation of e power ty, my of t. That's it. mx plus y of t is equals to mx of t into my of t. Right. Let us go for third property. which is very, very important for our examination. Third property, which is known as effect of change of origin and scale, which is known as effect of change of origin and scale. One of the very, very, very important property for 5 mark section. Number of times repeated question. Write and prove or state and prove the effect of change of origin and scale of the random variable capital X according to MGF. This is the very, very important question for your end semester examination. What is the statement of this one? The statement of effect of change of origin and scale is if capital X is a random variable, if capital X is a random variable, then mx minus a by c of t, mx minus a by c of t is equals to e power minus at by c, e power minus at by c into mx of t by c, mx of t by c, where a and c are arbitrary constants, where a and c are arbitrary constants. Let us prove this condition. By definition of MGF we have, by using the definition of MGF we have, mx of t is equals to expectation of e power tx, expectation of e power tx. Replace the variable capital X, replace the variable capital X by using x minus a by c, by using x minus a by c. Let us replace the variable capital X by using x minus a by c, where a comma c are constants, where a comma c are constants. We get this one, mx minus a by c of t is equals to expectation of e power x minus a by c. So this is again nothing but, this is nothing but expectation of e power tx minus ta, tx minus ta divided by c. Again, already we learned this property, e power a into e power b is equals to e power a plus b, e power a plus b. So by using this one, it can be written as e power tx by c into e power minus ta by c, e power tx by c minus e power minus ta by c. This is nothing but expectation of, expectation of. And expectation works only on the random variable. Expectation works only on the random variable capital X. So this term e power minus ta, e power minus ta by c is treated as constant. E power minus ta by c is treated as constant. So it can be written as e power minus ta by c into expectation of e power tx by c, e power tx by c. That's it. Here you observe that. Here it is the term. Expectation of tx, e power tx minus ta by c, expectation of e power tx by c, e power minus ta by c. Here you observe that this term is minus ta by c, minus ta by c. And expectation works only on random variable. Expectation works only on random variable. It does not works on the parameter t. So e power minus ta by c is constant. So you can write outside the expectation e power minus ta by c into expectation of e power tx by c. So by using this one, you can write e power minus ta by c into mx of t by c. Therefore, mx minus a by c of t is equals to mx minus a by c of t is equals to e power minus ta by c into mx of t by c. This is known as moment. This is known as change of scale property, change of origin and scale on MGF. By observing this, this is the independent. I mean, MGF is, observe that, MGF is not affected. MGF is not independent. MGF is not independent of changing the origin, of changing the origin and scale, of changing the origin and scale. Observe that. It is also stated that MGF is clearly affected by changing the origin and scale. MGF is clearly affected by the changing the origin and scale. So if you replace the variable x by using another variable x minus a by c, then the mx of t can be changed like this: e power minus ta by c mx of t by c. That's it. Let us see the next property. If capital X is a random variable, and a comma b are any two constants, then mx plus b of t is equals to e power bt into mx of at. E power bt into mx of at. Again, very simple proof. By the definition of MGF we have, mx of t is equals to expectation of e power tx. Let us replace the variable capital X by ax plus b. Replace the variable capital X by ax plus b. If you replace the variable, then you get this max plus b of t is equals to expectation of e power tax plus b. So this can be written as expectation of e power tax plus bt. Again, it can be written as expectation of e power tax into e power bt. Already I said that expectation works only on random variable. It does not influence our e power bt, means e power bt is a constant. So e power bt into expectation of e power tax, that is nothing but e power bt into mx of at. So that's it. Max plus b of t, max plus b of t, max plus b of t is equals to e power bt mx of at. Here ax plus b you must write in the suffix. Here x is in the suffix part. That's it. These are the properties of moment generating function, and wish you all the best. Keep learning, and remember that MGF is one of the very important definition for your end semester examination, and the properties are also